second video for section 9.3, measures of regressions and prediction intervals. This is, I'll give you assignment 7 after we get done with this video, and I'm going to go back through a bunch of this stuff just very, very quickly, and then end up with a couple of new things, and we'll do some examples on this video also to try to help you. And then the assignments at the end, it's just sort of a short assignment. We'll probably do something with it as far as I'll probably send out so that you can, something so that you can check your answers and make sure you're doing stuff right. We went through all this, so I'm gonna go sort of quickly. Remember the 3 types of variation: total variation, explained variation, unexplained variation. Before you can find any of those, you have to find the total deviation, the explained deviation, and the unexplained deviation. And this is talking about how your y's from your data deviate from your regression line, or your prediction of what the y's should be. Things to remember again, remember with the subscript I are the original data points. X bar and Y bar are the means of the X and the Y given data. And then Y hat, when you're using Y hat, that's what you're predicting at a certain X value. So the Y hat's your prediction, and Y hat equals mx plus b. M stands for slope, b stands for y-intercept. For your regression line, it's your regression equation, or your equation for your line of best fit. Variation, regression, we talked about this. Total deviation is each y in the data minus y bar, so minus the mean of the y's. Then explained deviation is the predicted y minus the mean of the y's. And then unexplained is each y in the given data minus your predicted y. So those 3 things, those are important. They're in the chart that that's what we're gonna use a lot of. Total variation is the sum of the original y's minus minus the mean of the y's, all those squared, you add them all up. Explained variation is this, and again, these are all in our charts that we're going to deal with, so I'm going through them very quickly because I went through them last time. And then the unexplained variation, we talked a little about that. That's how you're going to find your SE, is by using that unexplained variation, your standard error of the estimate. Total variation will always equal the explained variation plus the unexplained. So we really don't have to find the total. We can find these other 2 and just add them up to find out what the total variation is if we ever need that. Coefficient of determination, again, that's your R squared. We talked about that. You can use your calculator, and I'm not sure how this got moved, but it did. You can use your calculator to find some of this stuff, and any of it that you know you can use your calculator to find, use it. All right? And there's going to be several things that we're going to talk about that you're going to be able to use your calculator to find. You'll just have to punch in something different and then be able to find it, and I'm going to try to explain that so that we can make this as easy as possible. We don't want to make it any harder than it has to be. So R squared is always the explained variation. Explained variation over the total variation. We probably don't want to find the explained variation and divide it by the total variation to find R squared, since our calculator is going to tell us what R squared is if we punch in all of the original data points into our list. It'll tell us what A is, what B is, what R squared is, and what R is. So we probably don't want to do that. And if we know what R is, then you can just square that number to find R squared. But you do have to be able to tell what that coefficient of determination tells you. And what it tells you is that whatever the percentage of variation that can be explained and what percentage can't be explained. So if our R squared comes out to be 0.64, that means 64% of the variation for the predicted Y's from the actual Y's can be explained, and 36% can't be explained. Again, one more time, I'll say R goes from -1 to 1. And remember, as we get closer and closer to 1 or -1, then we have a really, really good correlation. As we get closer to 0, it's a poor correlation. And R squared goes from 0 to just +1. As we get really close to 1 here, that means we have less and less unexplained variation, and we have more explained. As we get closer to 0, more unexplained, less explained. And again, as we're getting closer to these or this, whichever one we're doing with the R or the R squared, that means we have a better correlation. That means our X and our Y, or whatever our two variables are more closely related, and we can make better predictions. We did this example, I'm going to skip over it real quick. Standard error of estimate, we talked about this last time. That was your assignment 6, was to tell me what SE stood for. Standard error of estimate. This is one equation that we can use for it, and we're going to do an example using this equation, then I'm also going to do an example using the other equation. And again, this standard error of estimate just sort of gives us an idea of how good our predictions actually are going to be. The closer the observed Y values are to the predicted Y values, the smaller the standard error of estimate is. We're going to use this chart, and I think last time, if you wrote this chart down last time, I had a summation symbol right there. It shouldn't be there. That's should be at the bottom. So I messed up the chart a little bit, but we're going to use that chart. Another formula that we could use to find the standard error of the estimate is this formula. When I've done a couple of problems using the two different formulas, it comes out just a little bit different, but it's real close. So I don't care which one you use, whichever one you use, it's going to be close enough for me. I'm not sure which one's better, or if one's better than the other. Sometimes it's easier to use this one, sometimes it's easier to use the other one. Just depends on all that you've done. Standard error of estimate is a measure of variation of the observation made around the computed regression line. Just simply, it is used to check your accuracy of your predictions. So we're just trying to figure out how accurate really are our predictions using our regression line. The other table that we can use is this table that we use to find M, B, and R, which we didn't really use it to find M, B, and R. I showed it to you and stuff, but then we used our calculators to find all that stuff. But this table uses that second formula that I just had up there. We're going to use it on an example. Just some things, again, explaining the standard error. The smaller the value of the standard error of estimate, the closer the dots are to the regression line. If we get a standard error as 0, then that means we're perfect. and every prediction we make is going to be right on. And what we're doing when we're doing this is we're deciding the goodness and the representativeness, not good words really, of the regression line, but we're trying to see how good our regression line actually is at predicting information, and how representative it actually is of the entire population. Same chart. We went through this last time. 4 things to find the standard error. You're going to make the table, use the regression equation to predict the y values. That's probably the hardest part of doing all of this, is you got to plug in each y and come up with, each x and come up with what the regression line is predicting that y should be. Then you're going to, again, just finishing out the chart. Then once you finish out the chart, you're going to plug into this formula right here. That last, the last column in the chart is going to be the top part, and n minus 2, n is how many ordered pairs you have, so how many pieces of data are in your sample, minus 2, and then we just do that, and that gives us our standard error. If we use that formula, if we use the other formula, it's using the other chart. All right, this is part 2. On part 2, I'm going to do this example here just real quick. This example is already worked out. I'm going to work one out with you at the end of the video using 2 different forms, and also one other thing that we're going to learn. We'll do some problems with it. So it says regression equation for the gross domestic products and carbon dioxide emissions. We already done this, and we came up on one of the other videos with this equation for our regression line. Find the standard error of estimate. We're going to use a table. When we use that table, this is what the table looks like. We got all our x's in this column, all our y's in this column, and then this is the hardest column right here to do, because what you have to do is you have to take your equation, this equation right here, and you got to plug in each x to get the predicted y. So that equation's 196.152. Give me 1 second. So if we have that equation, y hat equals 196.125. Hope I wrote that right. No, 152. Times x plus 102.289. And all you're going to do, you're going to take each of these x's, you're going to plug it in there, stick all of that into your calculator, and it gives you out the predicted y for that certain x. Then you got to do it for the next x. Then you got to do it for the next x and the next x. And that's going to give you this y hat column. So these are the actual y's. This is your y sub I, and these are what you're predicting that y should have been from your equation. Then you take these 2 columns and you subtract them, and you get these answers right here. And whether it's positive or negative really doesn't make a whole lot of difference, because once we find all of those, we're going to square each one and then every answer. So we're going to square each one of these, and no matter if it was positive or negative, once we square them, the answer is going to come out to be positive. And then this column right here, we add it all up, and that gives us our unexplained variation in our data. So this one is 152,916.020898. Why the book didn't round that off a little bit, I have no idea. I would probably have rounded that off to like 152,916, and I would have been good with that. Now, if you're doing something major and you gotta be real precise, then that's fine. For what we're doing, I'm just worried about you understanding or having some idea what each of these things mean and how they are found. So next thing I'm gonna do, I know n is 10. I just found this, this is the number that came from that last part of the chart. And all I'm gonna do is I'm gonna plug in. That number goes right here in the top. N is 10, so it goes right there. 10 minus 2 is 8. When I do this, I go ahead and I just take this number divided by 8. And then I remember that number, it's on my calculator. And then I punch in second square root and whatever that answer is. And that gives you your standard error. So we're saying that the standard error is about 138.255. And what that means, the standard error of the estimate of carbon dioxide emissions, when you write this, when you're explaining it, you're saying exactly this. The standard error of that's going to be first every time. And then what comes next is what your Y values stood for. And then what comes after that, then it says that's your Y values right there. Then it says 4A, then this is your X values, whatever your X value stood for. And then you just put is about whatever the number is. So this is the same every time. When you're explaining the standard error of the estimate of then you put what Y stood for, 4A specific, then what X stood for is about whatever your standard error came out to be. I'm not so real concerned about you being able to do all that explanation or understand all that explanation right now, just so that you have some idea. The next thing, two variables have a bivariate normal distribution if any fixed value of x, for any fixed value of x, the corresponding values of y are normally distributed. Notice that these are normal curves, but they're turned sideways to show the normal curve for the y values in here. The corresponding x values are also normally distributed. When we're talking about this, again, this is not something that I'm real worried about. Bivariate just means the two variables are related to each other somehow. All right, so that's all bivariate means, just that we're relating these two variables. If it was univariate, that just means that you just have one variable. So bivariate is just talking about how they're related. And this is just leading us into, we're not going to do a whole lot with this, so it really doesn't matter. But you do need to know what bivariate means. What this is leading us into is that we're going to take this y, wherever this y is, and we're going to try to predict some interval for it and say we're 95% sure that our y is going to fall within this range. And that's what the next part is, a prediction interval. Prediction interval can be constructed for the true value of y. Given a linear regression equation, that's what we've been doing, and x sub O. This is the X that you're picking to make a prediction off of. So it's some X. It doesn't have to be anything that's actually one of the numbers in our data. We're just making a prediction off of some X. So if our X's are like 1, 3, 5, 6, and so on, and we want to predict what Y is going to be at X is 2, then that's our X sub 0. So that's the number that we're predicting off of. A specific value of X, a C prediction interval. C is going to stand for our percentage, and we're going to use like 95% or 99%, so on and so on. And this is going to use the T distribution chart that I will hook to Moodle also to make sure you have it. It's also in the back of your book. We've used the T, it's also in the packet that you should have somewhere. It's just the T distribution chart. It's table 5, I think, is what they call it. The T distribution one, we're going to use that, and that's where the 95% and the 99% comes in. And we've done these before with our intervals. So you're just going to take your predicted Y minus your E, which we're going to find here in a minute, and your predicted Y plus your E when you make this interval. So we're saying that the Y should always fall between whatever we get here and whatever we get here, once we figure out what E is. To find E, we're going to use this formula. This TC, this is our critical value, and we're going to find this TC on the chart. Our SE, we just figured it out. So we're going to have to find SE before we can do any of the rest of this stuff. 1 stays the same every time. N is the number in the sample. N here is the number in the sample. N here is the number in the sample. And we're just going to plug in for each one of these. Our X sub O, X sub 0 there is the X that we're picking. X bar is the mean of all the X's. The sum of all the X squareds, we're going to need that other chart again. And then actually we don't need that other chart. I'm going to show you something on your calculator where you can find that. And then the sum of all the X's squared. We can find the sum of all the X's, and we can just square that to plug in there. So it's a big long formula. It looks all crazy, but it's not really that hard to plug into. Probably the hardest thing is we have to find that number on the chart, and that's not real difficult. The point estimate is Y hat. That's what we're estimating at. So we're picking our X, and we're figuring out by using our equation here what Y hat is at that certain X, and then deciding that all the Y's for that X value should fall within this certain range at a 95%, or we're 95% confident that they're all going to fall in that range or something like that. We're going to do an example. This is the chart I was talking about. This is the T chart, or the T distribution chart. You should have it in the packet that I've given you. It should be in the back of your book. Also, I hooked one to Moodle. And all we're going to do on this, our DF, we're going to use our DF, and then we're going to use this top row right here. Like 50%, 80%, 90%, 95, 98, 99. We're going to use that row. Don't worry about the one-tailed and the two-tailed. That was for the other stuff when we did alpha. The other thing for degrees of freedom, for the degrees of freedom here, your column, it's actually n minus 2. You can't read that. Sorry. It's n minus 2 instead of n minus 1 for this stuff. So your degrees of freedom are n minus 2 for these intervals. On all the other intervals and stuff that we've done with the t-distributions and stuff, our degrees of freedom was always n minus 1. So first thing, and these are just a description of what we're going to do to construct a prediction interval. Identify the number of ordered pairs and find your degrees of freedom. That's what I just got done saying. So find your degrees of freedom, n minus 2. Use the regression equation and the given x value. So this is the x value that you picked. You wanted to predict everything from for x equals 2 or x equals whatever. And you're going to plug it into here for x, and you're going to figure out what your y hat is. Find the critical value. This is using the chart. Table 5, the t-distribution table. You're going to use your degrees of freedom and your C, which is like your 95%, 80%, whatever level of confidence that we want. Find the standard error. You got to go through and do that whole big formula that we just got done doing. Doing the chart and everything, and whichever chart it is that you decide maybe you want to use. Find the margin of error. That's this big formula. So we're going to plug in this stuff and do all that. Find that margin of error. Then once we find the margin of error, we're just going to say we're going to take our y hat, our predicted y, minus e, minus that margin of error, and our y hat plus e, and that's what we're going to say that our y has to fall in that range, in that interval somewhere. In the past, we've written some of them just using something like this instead of using the alligator mouse when we've done these intervals. I don't know that it matters. But I've never ever seen this one written this way, so it might be better off to write it this way. You know, it's just going to say something like 25, 72 or something. So y, we know y is between 25 and 72. We're going to do an example here. They've already went through and they've done a bunch of this, and what you can do to come up with this is on your calculator, anytime you're given a set of numbers, so you're given your list of numbers, your x's and your y's, whatever they are, you put them into your list 1, list 2, and remember back to what we did at the start of the year. If I just deal with the x's, just list 1 or whatever, I can go into stat, over to calculate, and number 1 on that is 1 var stats. This is what we were using at the start of the year. If we hit that and put in whatever list we put this in, so if we hit that 1 var stat and then put in list 1, and let me do it real quick on my calculator. It pulls up all this stuff for us. It pulls up x bar. It pulls up the sum of all the x's. It pulls up the sum of all the x squareds. All right, and those are the 3 things that we need. So sum of all the x's, that's right here. Sum of all the x squareds is right there, and x bar is here. We need all 3 of those things. All right, so that's, if we use our calculator, and when we get to these charts here in a minute, We can also do that same thing for y. We can, if we put this in list 2, then we can punch in stat 1 bar stats, list 2, and find all this same stuff for y. Now you'll have to remember that if it's your y, it's going to tell you y bar, the sum of all the y's, and the sum of all the y's squared. But if we're filling out those charts, then we could use that to make everything a little easier on us, instead of actually filling them out step by step. Another thing that we're going to have to do here, we're predicting at 3.5 trillion. Well, we're going to take that 3.5 and we're going to stick it in there for x, and that's going to tell us the y hat, the predicted y that we're looking at. That's the first thing I did here, and it came out to be 788.821. So that's our y hat. When we get down at the end, we're going to take that number minus e, and that number plus e. Your critical values, your degrees of freedom is 8. So if we go to our chart, our degrees of freedom are 8, and we want a 95% confidence level. So let's go back to the chart and see if we can find this. Just real quickly here, if I can do it. Probably can't. Should have just stopped the video. There's our chart. So we want a 95% and degrees of freedom are 8. So we're right here. A pen won't write on this. We're here at 8 and we go over to 95%. That's right here. And down to 8. So we're here. Looks like 2.306. So that's our critical value. That's our TC. T sub C. So we find our critical value, 2.306. That's what we said. Again, that came from the chart. Once we have the critical value, we have our y hat. Next thing we're going to do is we're going to go back and plug into, and I'm sorry, we already found our S sub E. We had our S sub E, our standard error from the other problem, so we're just using that, and we're going to plug into this big long formula. You'll have to work it out again. We've done formulas like this in the past. You'll have to work it out how it's the easiest way for you to do on your calculator. My suggestion would be to try to do everything under the radical. Just looking at this, I would maybe do this part, write it down. So write down that answer. Then I would do this top part right here, leave it in my calculator, put parentheses around all of this, and just take this answer and hit divided by and put parentheses around all this and do all that together. Then you have that answer, and then I would just say plus whatever you came up with here, and then you would write down that whole answer. And you got to take the square root of that. So then I would take the square root of that. Once you take the square root of that, the hard part's over, because then all you got to do is hit, you got that answer right there in your calculator, you hit times, and you punch in this number, then you hit times again, and you punch in that number, and it's going to give you your E, which is 349.424. And again, if you round these off a little farther than the books round them off, that's fine with me. I don't know why they're going out so far on some of these. So we find our two sides, we take our y hat minus our e, we get this. We take our y hat over here on the other side, take our y hat plus our e, we get this, and that tells us that we're 95%, or you can be 95% confident that the gross domestic product is, if the gross domestic product is 3.5 trillion, that the carbon dioxide emissions will be between those two numbers. So we're 95% confident that it's going to fall in that range. This is just a quick summary. I'm not even going to worry about the summary. I'm just going to do a couple of examples. I changed my mind. Actually, this is your assignment, and this is assignment number 7. So assignment number 7, it's on page 519. It's not real hard. These first 4 here, really easy. The hard ones are 14 and 16. And then you're going to use 14 to help you with 22. 14 and 16 are finding the SE. That's where you got to use the charts. And then 22 and 24 are finding the interval. And so you've already done the hard part because you've already found the SE. 14 goes with 22, 16 goes with 24. I'm going to make a separate video. I'm going to separate these two videos. The separate video will have a couple of examples, about 3 or 4 examples of me working out a couple of problems. So I'm going to stop this video and then I'll make a separate video for the examples.